Here's 2016 free response questions. Somewhat to do with intermolecular forces, some old stuff too. First thing, write the electron configuration for an Na+1 ion in the ground state. So if we wrote sodium 1s2, 2s2, 2p6, 3s1 is sodium, but not a sodium ion. A sodium ion has lost electrons. You want to get rid of that. Using principal atomic structure, explain why the sodium ion is larger than the lithium ion. Well, lithium ion would be 1s2, and that's it. So a lithium ion has one less energy level, or a sodium ion has one more completely full energy level. So its electrons are farther from the nucleus, has a larger electron cloud. Which salt, LiCl or NaCl, has the greater lattice enthalpy? And it tells you, usually it tells you what lattice enthalpy is in here, but lattice enthalpy is the energy it takes to break the ions apart. Energy it takes to break the ions apart. So is it harder to break apart LiCl ions or harder to break apart NaCl ions? Well, chlorine's the same size. They're both chlorines in there. Since lithium is smaller, it can get closer to a chlorine ion. So since a lithium ion is smaller, here's a lithium ion, sodium ion. A lithium ion is smaller, can get closer to chlorine ion, and has more Coulombic attraction to that negatively charged chlorine ion because it is a closer distance away. They both have a positive 1 charge, lithium and sodium. Tell which one is sodium, which one's chlorine. Chlorine is a larger ion than lithium, so this would be your Cl negative, that would be your Li plus from there. It does ask at some point in time, what interactions, if this was dissolved in water, it splits apart into its ions, what interactions would there be between these ions and water? Between these ions and water would be ion dipole forces. This positive lithium would be attracted to the oxygen end. This negative chlorine would be attracted to the hydrogen end. Ion dipole forces. All right. Well, let's see if we got anything else on here. We're going to skip that. We're going to skip that. Might be all we do. All right, here's a quick question. 2014. Student places a mixture of plastic beads consisting of polypropylene, that's that, and polyvinyl chloride, PVC, if you've heard of that, the white plastic you see in a lot of times, in a 1 liter beaker containing distilled water. After stirring the contents of the beaker vigorously, the student observes that the beads of one type of plastic sink and the other plastic float. Telling why. And the reason I'm talking about this one is a lot of people think this is an intermolecular forces question. It's just a buoyancy question, just a density question. So things more dense in water sink, less dense float. So if you're looking at these, trying to figure out which one is more dense, notice there's carbon, 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 connected to a carbon, connected to a carbon. This N means that there's a lot of this group. This thing is just repeated. Same thing here, that is just repeated. So notice this one has CH3 groups, and this one has chlorine groups. Well, a chlorine is more massive, has more mass than a CH3 group, so this is going to have a higher density than this. This would be the one that would be sinking. That'd be the one that's floating. All right. One more question here. The boiling point of liquid propene right here is lower than the boiling point of vinyl chloride right here. Account for this difference in terms of the types of strengths of intermolecular forces present in each liquid. So why does this have a lower boiling point? Well, it's pretty nonpolar, so it only have dispersion forces between itself and like molecule. This up here, if you have lone pairs on here, as there should be, would have dispersion forces and dipole-dipole forces between itself. That's it.